So today we're very happy to have Andrew Lucas from the University of Colorado, Boulder, and he'll be telling us a bit about the hydrodynamics of kinematically constrained fluids.
Okay, yeah, so thank you for the invitation to come back and speak here post-COVID. So today I will talk about work on fluids with kinematic constraints. We sort of dubbed this Fracton hydrodynamics in 2020, but this offends some people, so I will not make that the title. Okay. There we go. Okay. So let me begin by first acknowledging various collaborators on this subject. So this began in work with Rahul and Andrei Gromov in 2020. And then more recently, I've been working with Paolo Glorioso, who was a former postdoc here now at Stanford, my PhD students, Jing Kang and Xiaoyang, and then Joaquin Rodriguez Nieva, now at Texas A&M. And funding from various agencies is also acknowledged. So roughly, the outline of my talk will be as follows. I'll sort of begin with a couple of comments about hydrodynamics from a sort of modern perspective, at least in my opinion. And then I'll sort of talk about three increasingly complicated and subtle realizations of fluid dynamics in the presence of sort of non-trivial constraints. So these will be sort of fluids with dipole conservation, and then same thing but without time reversal symmetry. And then lastly, I'll talk about fluids that have both dipole and momentum conservation, which leads to a sort of very exotic story. Okay, and maybe I should mention before I begin that sort of, this work was motivated largely by thinking about these questions because we could, and then sort of at the end we found some reasons to justify it. Yes. Let me begin by just some general comments. So, a story that we could have told in 1900, but, suppose we want to understand the dynamics of air molecules in this room. And the air molecules in this room, let's say they're classical, they obey F equals ma, so it's trivial, this is freshman mechanics, until we realize that there's, 10 to the 30 of them, and we can't put them on a computer. And so if we can't solve this problem analytically, then, if I want to understand practical questions about the acoustics of this room, for example, what can we do? And of course, the answer to this problem has been known for a long time, which is that if faced with a problem of many interacting chaotic particles, like the air molecules in this room, or whatever room you're sitting in if you're on Zoom, you can essentially coarse grain out the sort of microscopic degrees of freedom, very much in the spirit, or really exactly in the language of effective field theory. And you can integrate out, everything except for a small number of degrees of freedom that will correspond to conserved quantities and Goldstone bosons if you have spontaneous symmetry breaking. But these hydrodynamic modes form our emergent degrees of freedom, and they are described by a universal field theory called hydrodynamics, which is independent of microscopic details, in the usual sense of an EFT. Okay. For hydrodynamic EFTs, the small parameter that governs the regime of validity will be the ratio of a sort of microscopic length scale, which is a mean-free path when you have well-defined particles that collide off of each other, like air molecules. And you divide that by the length scale that you're interested in studying the system on. And so as long as this ratio of length scales is very small, or the box size is very big compared to the mean-free path, then hydrodynamics will be a good approximation for the resulting dynamics. And I'd really like to emphasize that it's not just a theoretical story. I mean, hydrodynamics really does appear all over the place in very different areas of physics. So, going back hundreds of years, we've studied hydrodynamics in gases and liquids, air and water. But in the past few decades, physicists studying quantum phases of matter have sort of rediscovered hydrodynamics multiple times. In ultra cold atoms, so the picture here may not be very inspiring, but it's a very nice experiment if I copied from the right paper at any rate. But the experiment I have in mind is that you have a bunch of cold atoms in a trap. You let the trap go and you ask sort of how does this cloud of atoms expand? And the expansion that you see is not equivalent to just a bunch of free atoms moving ballistically apart. You see that this cloud of atoms expands as a fluid with strong interactions and obeying hydrodynamic equations. In quark-gluon plasma that's created in heavy ion collisions, there's evidence for viscous hydrodynamics. Don't ask me much more about that system. I don't know much more than that. And most recently, starting in about 2015, there's been a lot of experimental work to see viscous electron flow in high purity solids, graphene, and now some 3D Weil semimetals as well. And in all of these systems, you are looking for something that's the Navier-Stokes equations or a sort of simple spin-off thereof, like relativistic Navier-Stokes. This talk will be trying to find a new kind of fluid dynamics because we've already learned a lot about this kind. But before I describe sort of how we'll discover new kinds of hydrodynamics, one sort of more piece of the lore that I'd like to emphasize is that as an effective field theory, we can ask very systematically questions about the stability of hydrodynamics as a fixed point. So when we talk about hydrodynamics, the fixed point we have in mind will usually be Gaussian. So you have sound waves and diffusion modes together with stochastic fluctuations that are required by the fluctuation dissipation theorem. And you can ask whether this fixed point has any relevant perturbations to it. And you find that for the Navier-Stokes system, that in 1 and 2 spatial dimensions, or 1 + 1 and 2 + 1 dimensions, if you prefer, there are indeed relevant perturbations, marginally so in 2D, but strongly relevant in 1 spatial dimension. The relevant perturbation is this quadratic nonlinearity in the pressure in the density variable. Here, just think of rho as being expanded around some constant which I've set to 0. So in 1 dimension, this is a relevant perturbation, and it will drive the hydrodynamic theory to something that looks very different from the Gaussian fixed point. In the Gaussian fixed point, in 1 dimension, the sort of effective particle of this theory is the sound wave. And what you find, if you follow the sort of RG flow, is that you land on, rather miraculously, we know what you land on, and the RG flow will land on the Carter-Parisi-Jean fixed point, which is a sort of classic dynamical universality class from non-equilibrium StatMech. So the details of how this works are not so important for today, but I just want to emphasize that there's both the question of what is the form of these equations, so we'll talk about that for more exotic fluids later in the talk, but we also should ask the question, when does this hydrodynamics exist? When, if you do a numerical simulation, will you see the sound equation, or rather that the solution to these PDEs describes correlation functions in your system. And sometimes you will find that that's not the case. For example, if you take a 1-dimensional chain of interacting particles and you look at correlation functions of the density operator, you will not see that that correlation function is given by a solution to the hydrodynamic PDEs. So in this plot, what you're seeing is that basically the correlation function, there's sort of a ballistically propagating piece, and if you subtract that out, this correlation function broadens with exponent t to the 2/3. And that's precisely the same exponent as predicted by the KPZ fixed point. So this is not a theoretical, construct. This is well, it is at first, but you can actually see this in numerics on a laptop. the effect is quite striking. Okay, so now I want to turn to the sort of simplest story about a fluid with kinematic constraints. And we can ask the question, what is the resulting hydrodynamics and what's the point of doing this? But okay. So firstly, let me introduce sort of what do I mean by hydrodynamics with a kinematic constraint. And the first example we're going to talk about is the hydrodynamics of particles that hop around on a lattice. So unlike the Navier-Stokes system, this will not be something in the continuum. There won't be momentum conservation. We'll come back to that at the end of the talk. But for now, we just have particles hopping around on a lattice. But in addition to maybe conserving the total charge or total number of particles, if you prefer, in addition to that conservation law, suppose that we add some other microscopic rules to the dynamics. So a particularly simple kind of rule that we could try to add is to say this isolated charge cannot move because the only moves that we're going to allow between the charges on our lattice are the moves that preserve both the total charge and the total dipole moment of this system. The dipole moment here is just sum of q times x over all the charges in the system. Obviously, that will forbid any single excitation from moving because that would change its dipole moment. But you can find little pairs of particles, in this case maybe a positive and negative charged particle, that can move together. This is a bit like a bound dipole state. You could also have two plus charges that move apart, or on these four sites create a minus plus plus minus out of nothing. Those would all be allowed. Okay. So this is where the jargon sort of annoys people. When we first started thinking about this problem, we decided that it would be good to brand this as fracton hydrodynamics, since fractons was a sort of sexy topic in the literature at the time and probably still is. And I think that was a good branding choice, so I have no regrets. But some people object to this phrase. Yeah, you can ask me more if you want afterwards. But so we said that because this individual excitation is immobile, it's a fracton, and thus the fluid dynamics of this kind of particle would be the fracton fluid. Okay. But at a minimum, you can say this is a fluid with some kind of kinematic constraint, that individual particles are immobile. Okay.
So dislocation moving would be an example of this because your dipoles have disclination.
Yes. Yeah. Leo has papers on thinking of disclinations in solids this way. So. Okay. So this is the setup. What happens? Well, if we didn't have this dipole conservation requirement, if we said the only thing that we require is that the charges on this lattice, can hop around, but the total charge needs to be conserved, we would just have Fick's law for diffusion. In fact, this is like the absolute simplest theory of hydrodynamics out there. And it turns out if you add dipole conservation, it changes going from 2 derivatives to 4 derivatives. I'll explain why on the next page. But so that sort of simple microscopic criterion, which you might think shouldn't really do anything to the macroscopic dynamics, actually has a quite important consequence. Okay.
What's the significance of the sign there?
Because it's a dissipative theory. So if you Fourier transform, you get minus k to the 4.
So B is positive.
Yeah. So yeah, after we predicted this result, which I think means we just scooped a bunch of people on this, but anyway, 2 weeks after our paper, a pair of works came out that simulated this problem of basically taking classical Markov chains where the update rules conserve charge and dipole. They ask what happens at late times. You can look at, for example, 2-point functions of the conserved density, and you find that they decay with exponents consistent with this subdiffusive equation. Okay. And these are not difficult numerics to do. I actually had a sophomore that reproduced these results. So, yeah. Okay. Why do we get subdiffusion? So why does this sort of simple microscopic update rule, why is it so dramatic? Let's focus on one dimension for simplicity. It kind of captures the argument well. So in one dimension, by conservation of charge, we know that we have this kind of continuity equation. Even in quantum mechanics, this holds. Now, we also want the dipole moment to be conserved. And in terms of the hydrodynamic variables, the dipole moment of the system will be the integral over space of the density rho of x multiplied by position x. So we need to take the time derivative of this object and set it to 0. This must be true in order for us to have correctly implemented dipole conservation. So we plug in this equation into the next line, integrate by parts, and we say that if this integral vanishes, we should take jx to be a total derivative. Okay? And so actually, our word identity for this theory is sort of unusual. We say that dt rho plus the second derivative of a current with 2 indices now has to equal 0. This is the consequence of dipole conservation. Now at this point you might say, well, so what? Because why don't I just set jxx to be rho? And what's the problem with that? That would lead me back to Fick's law of diffusion. The reason that you can't do that, or at least one reason, which we'll come back to a little later more carefully, one problem with trying to set jxx proportional to rho directly would be that j is time reversal odd, right, according to this equation, and rho is time reversal even. I mean, we could have taken it to be odd, but then j would be even, so the argument works either way. Okay, so now we have an odd current and an even density, and we need to make sure that this parameter a will exist. Okay? And let's for the moment say that we've got microscopic dynamics that has time reversal symmetry. In the Markov chain context, you simulate a Markov chain of particles moving around on a 1D lattice. And this is just the statement that you have a detailed balance condition on your update rules. So it's sort of mild. Many systems would have this property. But if you have that detailed balance condition, there's basically no parameter in the microscopic theory that's odd under time reversal. Okay? And this jxx is kind of like a thermodynamic variable, And so jxx, if it was proportional to rho with some coefficient a, that a would need to be expressible in terms of parameters in a microscopic Hamiltonian, etc., and none exist that are time reversal odd.
So A is different from this capital B,
Yeah. These are like two phenomenological coefficients.
but B doesn't have to be 0?
Yes.
How does this, it's the same A rho and B.
So that's a very good question, and I'll give you, I think, a more careful answer in the next part of the talk. But I would say this indeed sort of bothered me at the time, but with the benefit of hindsight, we sort of knew we needed to put this paper out because we thought we would get screwed. And so, anyway, which was correct. Okay, I'll explain why B is okay and A is not later, but Landau's sort of argument, I think, with historical revisionism at least, would be that at ideal fluid order in hydrodynamics, so lowest order with no derivatives in these currents, you have to respect time reversal. And all derivative orders after that doesn't matter. And I'll give you a better answer later on, but yeah, that was sort of what we said at the time. Actually, we did a little better than that, to be fair, but yeah, I won't explain sort of the other side of what we did because I'll just give you a clearer argument. Okay. So one other sort of technical or maybe conceptual question you might have is, okay, if I have two conservation laws, I have charge and dipole, why did we only talk about one density that's conserved? Why not talk about a dipole density? And the answer is because dipole density could not be a degree of freedom, at least not in general. So here imagine I have, I've coarse grained up space into different boxes, in the right box, I have a bound dipole state, right? And this is an allowed move. It conserves charge and dipole moment. And on the left, before the green arrow, I have one bound dipole state. And on the right, I have none. Okay. So there's no way that in a generic system with one of these multipolar conservation laws, you can't cleanly sort of separate out what part of the dipole charge comes from some fundamental bound object and what part of it is just due to the arrangement of charges. Okay. So in general, you're never going to add one of these kind of funny multipolar conservation laws and get new degrees of freedom. If this argument feels a little bit fast, you might feel at least a little more happy knowing that you can think of angular momentum density as a sort of antisymmetric combination of momentum dipoles. Okay. So actually a dipolar conservation law is not unfamiliar at all. And it's known that in the Navier-Stokes equations, you don't have an angular momentum density. It's at least not a long-lived hydrodynamic mode. Okay. And it's sort of analogous, it's really exactly analogous to this problem, at least the absence of a new degree of freedom. Yeah.
Could you explain why this argument doesn't also hold just for charge? So if I zoom out a little, I had 2 pluses and 1 minus charge. I zoom out a little, that looks effectively just like a single plus charge.
Oh, because it's 2 minus 1 equals 1. So indeed, the number of particles is not a conserved quantity in this system. It's that mode would have a finite lifetime. So, yeah.
Isn't the rule just that you're supposed to count conserved currents, not conserved quantities? That's always the rule with Goldstone modes.
Well, there's no spontaneous symmetry breaking in this problem.
Well, but hydrodynamics is kind of like the effective theory of currents. So isn't it just, aren't you just supposed to get one variable for each current? That's what explains the stress tensor case too.
Maybe, yeah. In real time, that sounds reasonable, but I'm not going to say 100%. Can think about it. Okay.
I have a question from out there. So if you want to use the analogy with angular momentum conservation, what's the analog of that? Is there any analog to suppression of some of the terms, like this A rho term in this situation? What is the effect of angular momentum conservation on the hydrodynamic equations that you think would be analogous to what you are describing?
I'm not sure if there's a sort of, okay, so the simple story about angular momentum density in Navier-Stokes is it makes the stress tensor symmetric. And here, the consequence of dipole conservation is a little more drastic. It basically blocks any term that doesn't have derivatives in the current. So it's, maybe what you can say is that you could write down an antisymmetric term in the stress tensor of an ordinary fluid as long as it had spatial derivatives. And the requirement that you needed spatial derivatives to do that is the consequence of angular momentum conservation. That's maybe the closest thing you can get to, but maybe there's something more clever that I can't think of. But,
Thanks.
okay, moving on. So, actually, we did have some inkling when we started thinking about this that there were at least some post-dictions we could make. And there are some funny places that dipole conserving systems show up, at least approximately, that you might not expect at first glance. One of them is in the quantum Hall fluid, at least in some sense. But a sort of crisper example arises if you take some simple Hamiltonian system and, here, for example, I have a Fermi-Hubbard model realized in ultra-cold atomic gases, and you tell the grad student to pick up the experiment and hold it at an angle. That's not actually what they do, although they do physically tilt the device. Anyway, so you physically tilt an optical lattice, with ultra-cold atoms obeying a Fermi-Hubbard model, and you modify the Hamiltonian to basically get some potential energy due to gravity. And at long wavelengths, you find that energy, so naively, without this red term, the hydrodynamic theory for this Fermi-Hubbard model is two diffusive modes, one that describes charge and one that describes energy. And when you apply this tilt, you find that the hydrodynamic modes morph. So one of them picks up a finite lifetime, and one of them becomes subdiffusive, k to the 4. And if you sort of track carefully through the calculation here, what you find is that the energy current becomes essentially this dipole current JXX up to a factor of 1 over F. And the rough reason is that the Hamiltonian on long scales, right, is dominated by this F term because it's super extensive. So in the thermodynamic limit, this F is really important, much more so than anything else. Everything else is bounded because this is a lattice problem. There's no infinite kinetic energy to draw from. And so as a result, basically energy conservation is dipole conservation up to subleading effects. Okay. And that explains why you must see k to the 4 subdiffusive relaxation of charge in this model. And this experiment was done half a year before our paper. And they indeed see that at no tilt, if you basically put in a fluctuation at fixed wavelength and ask how long it decays, the decay time of a density fluctuation will decay as lambda squared. But when you make the tilt larger, it grows to lambda to the 4. And this crossover is entirely a finite size effect. Just the experiment has a finite size, finite grant. Okay. So
Hamiltonian looks not unbounded from below, or is it just an illusion?
finite size, it's bounded. But it is, I mean, maybe even more weird is that the Hamiltonian doesn't scale with L. The maximum eigenvalue is minus L squared.
And what
But doesn't the ground state then, isn't it subject to some finite size effect of the low energy physics? I'm very confused about that.
So what I would say is that if you don't prepare the system in a state where like all the particles have fallen to the bottom of the trap, basically like you prepare yourself in an energetic state, you won't ever get to that sort of pathological state with energy of order L squared.
So this hydrodynamics is about high energy states?
Yeah, it's about typical states in the spectrum.
I thought we're usually looking at small fluctuations above the lowest energy states when we're talking about continuum hydrodynamics.
No, it also holds for typical high energy X state. I mean, you can take a random state in the spectrum.
Wouldn't a typical high energy state be an RMT state, not a hydrodynamic state?
Well, but if you ask questions about, okay, so if you take a model with a conserved quantity, infinite temperature, and you ask how long does it take if I, apply an operator that inserts one charge in the middle of the lattice. You can ask how long does it take before the correlation function, rho of L comma T, rho of 0, 0 isn't small. And that time will scale as L squared, even in a infinite temperature system. If you define the right correlation function, at least. Don't look at the retarded Green's function because that one will vanish at infinite temperature. But yeah, no, I mean, this is really a statement about typical states in the spectrum.
What is the role of temperature in this system?
Nothing as far as, I mean, if you want to get to this subdiffusive hydrodynamics, you actually want to be at beta equals 0 to make sure you're precisely looking at typical states. Because this energy is super extensive, right? The moment you turn on finite beta, you really need to worry about these rare kind of states where all the particles have fallen to the bottom. They can quickly dominate the partition function.
Does the dipole conservation hold at finite beta, or is it only the
It's exact. Oh, sorry. In this problem, it's at no. It should still be. It's still an emergent effect at sufficiently long scales.
Long compared to what?
So if you look at, okay, so in this problem, it would be, I think, 1 over F, basically. Once this red term sort of so think of it as like the maximum kinetic energy in this problem is 1. And so a particle can move a distance 1 over f and then it gets stuck. It can't go any farther because it can't get any more kinetic energy. And sort of that's the scale beyond which energy conservation looks like dipole conservation.
So, and another question, is this system a conductor or insulator?
In the experimental regime, it's a conductor.
So if I think of F as a essentially electric field, can I? Is that?
Yes, in that case, what we're looking at is sort of a regime at large scales where the electric field would drive block oscillations.
But right. So so it's a conductor with a current which flows through it, DC current, or is it insulator which is placed in electric field? That's what I'm trying.
Sorry, no, but, well, locally the system. So when f equals 0, the system is a conductor. At finite f, I mean, the system cannot propagate charge because of the like you can't put a lump of charge on one end and have it flow to the other because of dipole.
So it is.
Oh, sorry, if that was your question, it's certainly.
Yes. So at f equals 0, is this system insulator?
When f equals 0, it's a conductor at infinite temperature.
So that means that if I apply F, there will be a current proportional to F.
Within linear response, sure.
Yes.
But when f is large, basically, imagine
What happens to this current when F is large?
Okay, sure. So imagine you put a particle at like the top of the tilt, right, at the top of the potential, and you might think, oh, it's going to fall all the way to the bottom. However, if you put a lump of charge all the way at the top, it will sort of start falling, and then eventually it's picked up so much energy it can't get any more kinetic energy. There's just not enough energy in the there's no more kinetic energy left it can get because this model has a dispersion relation that's bounded from above. And once that happens, this lump of charge will just stop, and it will oscillate back and forth.
I'm not sure. The way I understand this is that what happens. That's what I'm trying to get. If that's what you are saying, doesn't it mean that you basically have one band which is where within which this charge accelerates, right? But because it's a periodic lattice, it basically goes to the end of the band, right? And then just comes in from the other side. So it oscillates between.
Sure, but okay, so this is like if you solve the classical Hamiltonian dynamics, what you see is that the particle oscillates in a fixed, sort of around a fixed position in space, and the momentum indeed grows unboundedly. But that's okay because energy is like cosine p.
No, but in this system, momentum cannot grow unboundedly because it's periodic, isn't it?
No, you have a finite, like the experiment is finite size, it ends at some point.
Well, it has nothing to do with the finite size. I'm talking about the lattice discreteness.
Sure, okay, but okay, in this sort of cartoon model, there's only one band, right, in this periodic system.
Yeah.
And they realized this experimentally. I mean, here's the data. So. All right. Anyway, let me continue.
Yeah. Okay.
Let me continue on. Okay. So now that I've sort of sketched out the simplest theory that has subdiffusion with dipole conservation, now let's talk about adding time reversal or breaking time reversal symmetry in these problems. And I would say the motivation for this is first and foremost, we just want to understand better this argument for why we got rid of A. You can actually do numerical simulations. You can try to break detailed balance. And we found that you can't ever get this A term that's non-zero. You always just get the fourth order term only. And so we thought about this question for a while, and we decided the answer is no, that you can't write down A times rho because A being non-zero would violate the fluctuation dissipation theorem. And then you might say, how can we say that? This system has no energy conservation and there's no temperature. And now I'm really talking, forget about the experiment. I mean, here I really have in mind just classical Markov chain on a computer. There's absolutely no notion of a Hamiltonian. There's discrete time update rules, right? Hydrodynamics is a sort of emergent description. And what we've sort of come to appreciate and maybe rediscover in some sense, sure not for the first time, is that there are EFT methods that really account for the non-trivial constraints from statistical physics, even in systems that are in no way thermal. There's in some sense emergent thermodynamics in a much broader range of systems than you might expect. And the key observation is that certainly for all the systems we would care about, but also I think many others, the dynamics naturally tend towards some notion of stationarity. So there's some, probability distribution on microstates such that if I draw from that distribution at time 0 and I ask what's the probability distribution at time t of states, it's exactly the same as the one I started with. And if you have this, then you can sort of think to 0th order that this capital phi is beta h. And now things you think you know from thermodynamics, you can kind of feed forward through and they will still make sense.
So what is the parameter justifying that approximation? Like,
Nothing.
in what regime is that accurate?
So it's a mathematical statement that, basically any sort of Markov chain or Markov process without with time independent update rules will have this stationary distribution. And under very mild assumptions, it will be unique. So there's really not an assumption about the form of this phi. You might ask, if I take the EFT limit, does this phi exist? And I would say we're just going to postulate it does, in the same way that you postulate a Landau free energy is reasonable. I think this is really not much more. It's really in the same spirit as that. For example, for the classical simulations that we do, typically phi is a uniform distribution on microstates. And then this capital phi we can estimate using the central limit theorem, basically, when we coarse grain out the degrees of freedom. So in that case, we actually know mathematically what capital phi is. Anyway,
But doesn't it require conservation law to limit the space of the microstates over which, like in the sense of ergodicity, right? That's what you are describing. Because
yes, so
if you take a system and it will distribute over all states regardless of their energy, I don't think this probability distribution will be even integrable, normalizable. Because the density of states could grow exponentially, right, with energy. So unless
fine. And so okay, there are two comments. So one is that the stochastic equation that would govern the evolution of this probability is linear. Like the Schrodinger equation is linear. So I don't really care about the normalization constant being awkward from that perspective. The second remark is like, okay, if I take a sort of standard assumption that this phi, for example, if I had energy conservation, and so I imagine that I'm sort of uniformly distributed on the shell and phase space that has fixed energy, then I would just say phi is, well, e to the minus phi is like a delta function of h minus e, that's fine. So everything from sort of textbook StatMech can be fit into this formalism, but I'm saying you don't need to have a Hamiltonian system to make sense of this. Like I can give you a Markov chain with discrete update rules, and I can find a stationary distribution and talk about its long wavelength limit. This is a perfectly well-posed calculation.
But for fluids, you need to fix the energy, right? Otherwise, this probability will not have a maximum. It would be just
Yes, for ordinary fluids, phi is beta h. That's fine. Okay.
Should it be just the entropy?
So what about entropy? I mean,
It's a number of states, right? So
yes, but what about it?
that minus phi is just the entropy.
It depends on what rho is. Okay, let me just continue. I mean, the point is that, okay, if you take a phi of this form, so this mu is a mathematical object that will show up on the next page, otherwise I would have ignored it. But there's a sort of emergent notion of thermodynamics that makes sense, okay, even if you don't have a Hamiltonian system. And the philosophy that we're going to use is that, sort of inspired by path integrals for classical stochastic dynamics that were developed by Martin, Sigia, and Rose, we're going to look for an effective field theory, basically that is consistent with certain symmetry principles that I'll elucidate. Basically the existence of this stationary distribution will play an important role in those symmetries, but once we sort of realize what these symmetries are, we can just turn the crank on EFT, at least in some ways.
S is the action for what? What is the relation between S and phi?
S and phi, I'll explain momentarily how phi constrains S. So S here, what the MSR path integral does is it gives you essentially a path integral representation for the transition probabilities between two microstates. And you express that as a path integral over fields pi and rho. So this was developed in the 1970s, but in that day, what people did was they would write down the differential equations and then build the path integral. And what we're going to do here is basically build the path integral instead from EFT, which is not that big of an advance, but okay, that's what we're doing. All right, so H, so the H that sort of shows up here, you can show that if you want to encode, for example, a hydrodynamic theory with charge conservation, you need to impose certain shift symmetries on pi. So if, for example, you want dipole to be conserved, then pi needs to be invariant under constant and linear shifts in x. Okay. And spatial symmetries are sort of straightforward. The interesting symmetry in this problem will be time reversal symmetry. So under time reversal symmetry, you'll find that pi, this sort of auxiliary noise field that you have to introduce to describe dissipative dynamics with an action, you find that pi will have to flip sign, but also shift by a constant offset. You can actually argue for this form of pi purely on EFT grounds, sort of the only possible Z2 transformation on pi that doesn't involve an infinite order Taylor series. But also you can check that when you make this particular choice, so remember here mu was defined in this way as a kind of quote unquote chemical potential. And with that definition of mu, you find that MSR's path integral obeys detailed balance. So this is precisely what we mean by time reversal in a sort of quote unquote dissipative system. You have time reversal symmetry when microscopically the probability to go from a microstate at time 0 to a different one at time t is the same as the probability to go the other way multiplied by the difference in sort of free energies, if you will, or more precisely the ratio of equilibrium probabilities. Yes?
Can I think about this P as something that you extract from the S on the slide before?
What is delta phi is some function of S there? I don't understand what the.
No, okay, so phi is back here. It's like the effective free energy, if you like. S is different. So S is the action that we're going to use to generate.
But isn't S the thing that generates the probabilities on the detailed balance? So isn't there therefore some relation between S and phi in order to make that equation true?
I mean, I'm not going to say they're unrelated. They're related in the sense that typically S will obey this symmetry. But there are multiple choices of S consistent with the same phi. So there's not a unique mapping between the two.
Wait, but if you have S, can you compute the P of?
Yeah, of course.
Is that what you mean?
Yeah, that's what I mean too. Yeah, that S you can compute P, so
Yes,
therefore you
that's
can
certainly
solve
true.
for delta phi in terms of ratios of something you compute with S.
So maybe one way I would put it is that That's typically the historical perspective that you'd say, here's my transition probability given here, and well, let me wing it and try to guess phi sort of the long way by put in all possible microstates and so on. What we do, which I think is a little more elegant, is to point out that usually we can kind of guess what this capital phi is, and then we can rule out sort of many terms in the action S that you might naively write down and show that they in fact would lead to sort of undesirable probability distributions. For example, in our Markov chains where we know what the stationary distribution is, this construction will tell us that not all terms in an equation of motion can actually exist, even if they're consistent at the equation of motion level with all symmetries that you can think of.
Okay, I'm probably just not understanding many things.
If you understand correctly, if this you require pi also minus pi plus I mu, so then you will get this detail balance with phi where mu is equal to derivative of phi over rho. That mu, if you put in this mu as a requirement for time reversal, but this mu actually is a functional of rho.
Yes, so mu is a functional of rho in general.
And the phi is
the integral of that, basically. Yeah.
Or your question is different.
I have a lot of questions, maybe. S is something local? I mean, what is the context in which we're applying effective field theory here?
So the goal is to write down a sort of local, so H is going to be local. I'll show you examples
Why
of
is
this.
it local?
Why is it local? Well, because the physics
Started with
is...
some kind of random Markov chain. I didn't even understand the assumptions, but why did you get something local?
So you get something local because you say my Markov chain, the update rules are spatially local, and they're certainly local in time by the Markov process, by the Markov assumption. So we should expect that the, differential equations that govern the evolution of charge are going to be local in space and time.
Are we trying to generate differential equations for hydrodynamics? Why are we doing a functional integral then?
So, okay. Actually, one way you can think about this, which I think is arguably better, is actually to say that this H generates the Fokker-Planck equation, and what we're really doing is sort of taking a certain classical limit where you can think of, it's sort of like a WKB-like limit, where this pi would be basically like dd rho, but you can approximate it, as like a classical momentum. This is one. But anyway, okay. Maybe let me just sort of explain.
There's noise in the hydrodynamic equation, so you have to have path integral to sum over different paths.
Anyway, let me just sort of highlight a little bit of how it works, but then I want to get to the last example as well. So if you have, for example, charge conservation in one spatial dimension, then the Lagrangian that you write down will be this pi dt rho term. And then if you demand time reversal symmetry and charge conservation, the only term you can write down at leading order will be this one with dx pi and dx pi minus I mu. The pi and pi minus I mu flip under time reversal. So that's why you need to have this structure. The I times sigma here has to multiply something positive, basically because, as Sam just said, integrating over pi is like integrating over noise, and this has to have bounded distribution. So we know sigma has to be non-negative, and then asserting that phi will be, if the typical density is rho equals 0, phi will be, by the central limit theorem, an integral dx of rho squared. This chi is charge susceptibility, the thermodynamic coefficient. And you throw all of this together, and you find that you get the Einstein relation that relates conductivity, diffusion, and susceptibility. And you get a fluctuation dissipation theorem, which is the proportionality of the coefficient between pi squared and pi mu. So all of these facts sort of come for free from this stationarity assumption. You don't need to assume anything about the system being at finite temperature, etc. All right, maybe let me skip a few other examples. other than to say, when you start breaking time reversal, we can now systematically analyze, add dipole conservation, relax the assumption of time reversal. It turns out there's only one new term you can write down, which is this dx mu dx squared pi. And the consequence of this is that no matter what symmetries you break, you can never write down this jxx proportional to rho term, even without time reversal symmetry, without parity. That term is forbidden basically because if you added it, you could not find a stochastic process with the correct stationary distribution, which is local. So under the assumption that the system relaxes to a sort of featureless state, you can rule out, using our formalism, the existence of these low derivative terms in the hydrodynamic equations. And you can do the same thing with quadrupole conservation, and you can keep going to sort of, conserve more and more multipole moments, and you basically just get more derivatives, and okay, but the story is sort of the same. Let me just quickly mention as well that in these systems that break time reversal, you can ask whether some of these terms we're adding to the hydrodynamic equations cause a breakdown of the Gaussian fixed point. And the answer is yes. Okay. And we've done numerical simulations where you can see that when time reversal symmetry is broken, you see strong deviations from the sort of detailed balance obeying scaling. Okay. All right. In the last 10 minutes or so, I want to talk a bit about systems that have both dipole and momentum conservation. So naively, again, we started doing this just because we can, and we said, why not? You take charge and dipole conservation that we've talked about, and now instead of talking about particles hopping on lattices, we have in mind sort of particles moving in a continuum. So we can talk about momentum being conserved, and we should anticipate that there will be another hydrodynamic degree of freedom, which is the momentum density. And you can ask about the algebra that relates the conserved quantities, and the classical Poisson brackets between them, or commutators if you prefer quantum mechanics, look like this. Importantly, there's a non-vanishing Poisson bracket between dipole and momentum. And as we'll see, this has very important consequences on fluid dynamics. Okay. So, the simplest thing you might expect, which is true, although not the whole story, is that you need to modify the Navier-Stokes equations to first and foremost make sure that the charge current has no zero derivative terms. So in the ordinary Navier-Stokes equations, you would write J is rho times V, and obviously that's not going to be okay, at least when V means something local, because then you would not have this sort of second derivative structure. But actually the most important consequence of this algebra between dipole and momentum is that if you ask how the momentum density transforms under a dipole shift, you find that momentum is not invariant. It will pick up a constant proportional to density. So here Ci is a constant vector. You can think of this transformation as like take your state and multiply by the unitary e to the minus I Ci di, quantum mechanics. Okay. And we find that when we do that, we shift the definition of the momentum density by a factor Ci times rho. Alternatively, if we divide out by rho, then this quantity phi will shift by a constant under dipole. And this means that everything in the theory, thermodynamics, etc., must be invariant under these constant shifts. Okay. And this is maybe a bit suggestive that this phi will be a Goldstone boson. And that is in fact the correct interpretation of phi. It's not obvious at this point, but I'll try to explain a little bit why that's the case. The hydrodynamics of this theory is complicated. There's a lot of tensors and so on. So you can see our paper if you care. At the hydrodynamic fixed point, the excitations correspond to sound modes. So that's in the first line. The difference with ordinary sound is that instead of k real dispersion, you have k squared, and the dissipative part would be k to the 4. And transverse momentum subdiffuses with k to the 4. Maybe the exponent's not too surprising because that's what we saw with just dipole. You can again do a scaling analysis and ask when there are relevant perturbations to hydrodynamics as an EFT. And you find that below 4 spatial dimensions, there are relevant perturbations. It's actually the same kind of perturbation that we saw before. And so there will be a sort of fracton-inspired generalization of this KPZ universality class in 1, 2, and 3 spatial dimensions. And we have seen numerical evidence for this quite strikingly. So we can simulate this classical Hamiltonian system with 1 or 10,000 particles. And this classical Hamiltonian system has both momentum conservation because it's invariant under shifting all the coordinates by a constant. And it has dipole conservation because it's invariant under shifting all of the momenta by a constant. And we can try to extract the exponent relating scaling in space and time by looking at the typical fluctuations, the wave number of typical fluctuations as a function of time. So we kick the system into a highly excited state, and we ask sort of at later times which of the initial fluctuations persist. And we find that depending on whether we include the most relevant nonlinearity or not, we find that the scaling exponent here, z, goes from either being close to 4 without the relevant perturbation to about 2.5 with a relevant perturbation. And so this, to us, is sort of strong evidence that, that we have indeed sort of landed on this non-trivial fixed point in our simulations. Okay. And as advertised, this fixed point also exists in higher dimensions, and you can just say that Joaquin simulated about 1 million degrees of freedom in 2 dimensions and found very strong numerical evidence for a non-trivial dynamical universality class again in higher dimensions. Yeah.
I just don't know much about this, but so this is all classical, right? What
Yes.
does this allow us to conclude about the like quantum EFT?
So I would argue that hydrodynamics as an EFT is basically classical. There's the regime where quantum fluctuations are important is sort of the Planckian time, which is probably not when hydrodynamics makes sense anyway. So even a quantum system will be described by this classical EFT once it's at finite temperature and in a hydrodynamic regime.
And sorry, the dynamics is governed by Hamilton equation with the Hamiltonian.
Yes. I mean, the 2D Hamiltonian is a little more complicated, but in 1D it's very simple. Actually, things very similar to this have been written down to describe quantum Hall fluids. Although there, this sort of funny kinetic term, instead they would write pi minus average momentum, which is totally non-local in space. But you just make that local in space and you get this local theory with dipole and momentum conservation. Maybe let me just say a few remarks about, we're currently sort of developing a geometric effective field theory for hydrodynamics in this system. This is sort of inspired by work done by Hong Lu in 2015, together with Paolo when he was a grad student. And one reason for this is, of course, just to check what we've done before to make sure it all makes sense. But also, this problem is of some interest because people have asked questions about whether it makes sense to study sort of fractons and constrained phases of matter on curved spaces and to couple these theories to gravity. And at least in this context, sort of we can say that this question makes sense. Okay. So you couple this theory to Vielbein. This is sort of more natural language to talk about this in. And basically, we add a gauge field for all of the U1s for charge and dipole, and if rotation invariant, a spin connection. Okay. And okay, let me just skip through. sort of complicated, and here are the equations of motion. One thing from the EFT perspective that's very clear is that there's this degree of freedom phi, which is actually the same as what I mentioned before. It's momentum density approximately over charge density. The way that this phi shows up in the EFT is as a phase field associated with these dipole, with the dipole symmetry. And yeah.
Why you need to turn on the torsion?
Why not? I mean, it's already a very general background, so we just went all the way, I guess.
So this is finite temperature or?
Yes, but it's a little delicate here because we don't want to talk about energy conservation. Energy conservation actually changes the universality class somewhat annoyingly. So we sort of ignore energy, but yeah, but you can sort of think of it as perhaps effectively finite temperature in the sense of this phi that I introduced earlier, but this is a sort of subtle point that I would say we don't fully understand. Okay, so if you don't care about the geometry, so I think this leads to some interesting observations. So as I mentioned, the momentum current, so here T0b, this is approximately rho times this dipole phase field. And the fact that the dipole phase field shows up in the action, or in the equations of motion rather, without time derivatives, and must show up that way. You cannot find a theory where this phi only shows up with time derivatives. This tells you from this EFT perspective that phi is a Goldstone boson and that dipole symmetry has been spontaneously broken. In the flat space limit, you can reproduce what we found before. For example, the charge conservation equation has this kind of funny structure with two derivatives on the current. And I think in the past, when people have tried to couple fracton matter to curved space, they try to generalize notions like mixed rank tensor gauge fields directly onto curved space, and it's a bit awkward when you do this. And I think our construction is a little bit more transparent. For us, we sort of don't start by making symmetry assumptions on the background. Those symmetry assumptions arise in the flat space limit because, for example, in this problem, if Jij had an antisymmetric part, that's fine, it would just decouple from the equation of motion. One final cool thing about this theory is that it has dipole spontaneous symmetry breaking. So there's a spontaneously broken symmetry even when it's naively forbidden by the Merman-Wagner theorem. So in and below two spatial dimensions, this phi has correlators that are like 1/k squared in momentum space. So phi correlators have no long-range order. And despite this, we still find that the symmetry is spontaneously broken. And I think, I don't care that much about the semantics. I think Seiberg and his crew is sort of unhappy with us, saying that this theory has SSB. But what I think is interesting is that this is a setup where there's a certain mathematical sense where symmetry is broken. You can't talk about states in Hilbert space that are singlets under the whole symmetry group. It's just impossible because the Heisenberg algebra has no trivial irrep. And at the same time, there are sort of large sort of Merman-Wagner fluctuations. Correlation functions in phi do not exhibit long-range order. Yeah?
So where's the loophole in the theorem? Or
so maybe one simple loophole, although unsatisfactory, would just be that phi is in R. It's not a period, it's not compact.
If I go to your initial Hamiltonian with the pi plus 1 minus pi, and if I promote it in 2 dimension,
yeah.
If I understand, you can make the Hamiltonian, the energy 0 by having everybody moving in one direction with the momentum equal to the other. So that's like,
yes.
like a little flock, and you bring.
Well, but nothing moves. So it has momentum, but nothing is moving, and that's sort of the key point.
Oh, okay.
That, right, this shift is basically the phi shift that
I see.
that we can sort of now recognize as the Goldstone boson associated with broken dipoles.
But the fact that everybody's aligned, that there is this finite, is that some form of breaking of Galilean invariance that kills Mermin-Wagner?
So certainly this theory
is
won't
that-
have Galilean symmetry. That's certainly.
Is that the reason why you can have this long, or you're saying I shouldn't, this long range order even in 2D, for example?
I guess I would say don't think of this theory as having long range order because
Even if you have all the p's pointing in one direction.
But if you look at fluctuations of that p, it's just like in 1D, you would not have long range order in a superfluid because fluctuations wash it out. Here, I think the sort of loophole is that phi is not periodically identified. So even if the fluctuations are long lived, its average is still sensible. And like you can talk about phi as an observable, whereas before maybe you have to talk about e to the I phi, which indeed washes out.
Is there any way to think of phi as a coordinate for some coset of the dipole plus momentum algebra? Or like if I take that algebra and do the coset construction by saying that there's some statements?
Yeah, we do that, and phi is the field associated with.
Okay.
So it's the coefficient in front of D in the
Right.
coset.
I see.
All right, anyway, since I'm over time, let me just put up some conclusions and end here. Thanks.
So, yeah, go ahead. I just wanted to go back to this question of dislocation, because metallurgists have been studying, relaxation in solid by motion of dislocations, and I guess naively the intuition that the dislocation is a dipole of 5 and 7-fold coordinated atoms is in the ballpark of what you mentioned at the beginning. If you look at this old effective theories for dislocation dynamics or crystal dynamics by Halperin, Nelson, Ambioker, all these guys, do those theories have essentially the same features that you highlighted in the beginning, like that diffusion becoming fourth order and derivative?
In some cases, I believe I don't remember. We have thought about it a bit, and I think in some cases they do, but I don't remember off the top of my head. There are certainly theories of. Okay, here's a simple example that I can remember. So if you have just even like a boring elastic plate, for example.
Yeah.
So in that case, you can think of the fact that you get omega is k squared as coming from. I mean, maybe it's a slightly different question, but it's the one on the top of my mind. So there are sort of exotic phenomena that you can kind of re-understand in this language. And I think I've talked with Leo about dislocate, like I think closer to what you mentioned. And I don't remember the answer, but I believe there are subdiffusive theories that we can understand in this language. Actually, someone else.
Because what I have in mind is not sophisticated at all. It's really two-dimensional crystallography.
Yeah, we should talk about it more. I don't remember, but I think if we look it up, we can sort of quickly diagnose.
What is the relationship between this fracton and the other fractons that people?
Oh, the other fracton.
Fractons in 3D lattice, do they also satisfy you somehow heat it up, heat this crystal lattice model up? Do they also form some kind of fractonic hydrodynamics like this?
Oh, you mean in a physical 3D solid?
No, in the
or
this X cube model,
Oh,
whatever the model that people.
Sure. So yeah, if you take the X cube model like that, also, I don't remember the exact symmetries that one had. I think it's got like dipole in some directions and not others. But you can frame it in this language, and I think actually in one of our papers we sort of mentioned the hydrodynamic theory, for a model with the sort of symmetries of the X cube model. So you can certainly extend this to higher dimensions. The new feature that I didn't talk about in this talk is that in higher dimensions, you can have what are called subsystem symmetries. And that also can be treated in this formalism And you get kind of peculiar, like dx squared, dy squared rho kind of subdiffusion, where it's very anisotropic. So yeah, we have some papers where we've talked about that extension as well.
If there are no more questions, let's thank Andy again.
And we'll also be doing a dinner with the speaker.
Yeah, when you are not interested, you
I'm very flexible, I can talk tomorrow and